In this video, we're going to look at how to evaluate the electric field from a line charge density using Gauss's law. To start, we recognize that the line charge density, or charge per length, is we can write it out as a charge density as a generic volume charge density, as a line density with appropriate delta functions. In this case, our situation looks like a line where the electric field, of course a line with a charge density, lambda, the electric field is coming off perpendicular to the wire in all circular directions. So it's coming off this way, if you can imagine that in 3 dimensions. This means that the Gaussian surface we want to use will be cylindrical. Now, of course, this is clarify, an infinite line charge. The advantages of that is, it means that the electric field lines are everywhere perpendicular to it. We don't have to worry about electric field lines coming out of these sides. Now, in practice, of course, we have no truly infinite line charges, but we can have line charges that are long enough to be effectively infinite. In other words, they're much longer than any of the other aspects of the problem. And these we can have in real life. Okay, so to start, we want to start with Gauss's law. We write out our volume integral with, that should be a Q over, well, we want our charge density properly. So we'll write out the volume of our charge density over epsilon naught d volume equals the surface integral E dot dA. Our charge density in this case will be lambda with these delta functions. Now we can work this out specifically. I'll leave that to the student. However, we can also look at this and say that the amount of charge in here is our charge density times the length. So we're going to say we have a Gaussian surface of a length L. In some area here, I'm not going to define, I'll simply call an area A, with a radius r. So A would have an area of pi r squared. Now, given this, the amount of charge inside here, the total amount of charge, which is what this is measuring, becomes lambda L over epsilon naught. Also, because the surface, as I said, the electric field lines are going perpendicular to this surface, they are parallel to this surface, which means, this is the part that makes it easy, we don't have to include the two ends. So we can take the electric field times this surface area. The circumference of a circle is 2 pi r, and the length of this is L, so the total area on the lateral area of a cylinder becomes 2 pi r L. Now, we notice that we have L on this side, we have L on this side. In other words, if we divide by L, L does not even occur in our equation. In other words, it doesn't matter how big or how small we make our Gaussian surface, because L is just going to disappear anyway. if I solve for the electric field, I can get electric field equals lambda over epsilon naught 1 over 2 pi r. And of course, this is all in a radial direction, coming off from the line charge. One thing to notice, we have r right here, not r squared. From a point charge, the electric field comes off and diminishes, it gets smaller, at a rate of 1 over r squared. That's what we usually deal with, but not when we're dealing with a line charge. In this case, for a line charge, the electric field diminishes at a rate of 1 over r. It diminishes more slowly. This is the correct electric field from the line charge inside, from the line charge.